Alright, so guys, jumping back into this, number 4, as we discussed yesterday, and we'll discuss, again, even more and further today. We are preparing right now, number 4. This is actually preparation for a multiple choice question. So no, you will not be asked to physically draw the graph. You may be given a graph and you're asked multiple choice questions about that, or you're going to be given some information and then you'll possibly, A is this graph, B is this graph, C is this graph, and so on, and it'll be up to you to pick. Okay, but what we're going to practice here in number 4 is looking at the graph and can we determine the equation. So various ways that we could approach the problem. I like doing it this way though, again, just try to stay consistent with how we kind of approach things all first chapter. But what shape is that? What do you see? It's a parabola, which means it's what type of equation? Quadratic. So if we think back to the parent function, f of x is equal to x squared. The parent function had the vertex at 0. We were over 1 up 1, over 2 up 4, left 1 up 1, left 2 up 4. And this was, again, roughly sketched in, this was the parent function. Okay? Now it's our job to determine transformationally, how did we go from vertex to vertex? What are we doing? Up, down, right, left, how much? What are you thinking? I think I heard you kind of whisper something. Right, how much? Right 2, good. Do we go up or down at all? Yeah, how much do we go down? Down 4. Okay, so if we move right 2 down 4, could we come up with the function here? I think so. Say that f of x is going to be equivalent to, if I'm moving to the right 2, that's going to be a subtraction within the parentheses. If I'm moving down 4, that's going to be a subtraction after the fact. But this is how we'd get there. Now, could we have looked at this as, all right, well, my vertex is at 2, -4, so h is 2, k is -4. Could we have done it that way also and built it out using vertex form? Please don't, hear this the wrong way. Yes, we could have done it that. I just feel like that would be more complicated. Okay, again, just one guy's opinion. I think it's always easier if we start with parent function and we adjust from there. All right, part B. What function are we tying back to here? What do you think? What do we have? Cubic. Good. So we're thinking about g of x is equal to x cubed. And again, there, our parent function is going to hit the origin. We're increasing, so left 1 down 1, right 1 up 1. And this is a very rough sketch of the parent function. So not only are we shifting, transforming vertex to, or I shouldn't say, it's not really vertex, I shouldn't call it that, but that central point, that critical point right here, we're transforming that, looks like right 2 up 2, but what else is happening? We're reflecting it, aren't we? So we said that we're going to move right 2, we're going to move up 2, but there's also going to be a reflection in the x-axis. All right, so how do we write that up, I guess is my question. So g of x is going to be equal to, so if I'm shifting to the right 2, what's going to happen? Just like before, I've got to subtract 2 inside of the parentheses. Still cubing that. If I'm moving up 2, what's going to happen? You guys are out there today, right? We're going to add 2. Are we done? Not quite. What am I going to do to showcase there was a reflection? I'm going to have a negative out front. Okay? Now, if I'm remembering correctly, guys, for whatever reason, we had people that have struggled in the past to remember to put the exponent there. I don't know why. I think we get so fixated on, okay, what's my transformation? I'm moving this much to the right, this much up, this much. Oh, this is a reflection. We can't lose sight of the fact, I should say, that if we neglect to put that exponent of 3 there, it's not a cubic function. If we had this squared, then it would have been a parabola. If you have, again, to the first power, well, now it's linear, and that's something way different. Okay? So again, we definitely want to pay attention to that. Obviously, it's important. We wouldn't put it there if it wasn't important. All right, so number 5. Number 5, it says, for f of x that we want to find the vertical and horizontal asymptotes. Now, if we're just to pay attention to the directions here, it's actually pretty telling. Completely leaves out slant asymptote. It just gives you the fact that there's not going to be a slant asymptote here. If it didn't say that, for instance, if it just said find all asymptotes, why is it that there will not be a slant asymptote in this situation? Vincent? I like the first part that you said. I wouldn't say anything about the leading coefficients yet, but the degree of the numerator is the same as the degree of the denominator. So for that reason, there's no slant asymptote. The only time that a slant asymptote is potentially going to be there is if the numerator's degree is exactly one larger than the denominator's. And in this case, that's not happening. They're the same, like Vincent is telling us. So we know that we're going to have horizontal asymptotes. In fact, Vincent has essentially already given us the key there when he mentioned the leading coefficients. If we ever find ourselves in a situation to where the numerator of the degree of the numerator is less than the degree of the denominator, then it's an automatic thing. Where is the horizontal asymptote automatically going to live if the numerator's degree is less than denominator's? Say it again. Yeah, y equals, again, the x-axis. Automatic, we don't have to think about it. It's never going to adjust. That's not the case here, okay? We have degrees that are equal to one another. So what am I going to do with my leading coefficients to find this horizontal asymptote? We remember? Yeah, we're going to set up 5 over 1. This is going to be y equals, by the way. So as we clean this up, y equals 5. Now, I'm right now realizing that maybe we should have done something else. I think it's because I've worked this problem before that I know that we don't have a situation to where anything's going to factor and cancel out. But shouldn't we have probably gone through that process first? We should have checked anytime we have these rationals. Can I factor the numerator? Can I factor the denominator and have a cancellation? We should always be starting there. I kind of jumped past that point because I'm just going to tell you right now, hopefully you believe me, that nothing is going to factor in the numerator that cancels in the denominator. Okay? Now, what if that would have been the case? Well, that would have thrown off the way that we have our horizontal asymptote anyway. So, yes, Will.
On the test, will there be any slant asymptote?
I'm going to say potentially, but also pay attention to the type of problems that we are focusing on. It's not an accidental. See how I'm saying something without saying something there? All right, what about vertical asymptotes? Vertical asymptotes. How do we go about finding vertical asymptotes? Yeah, we're going to set the denominator equal to 0. Once again, can't stress enough. If we had factors that were going to cancel, absolutely we would have taken that into consideration. But as promised, that's not going to be the case. So we're going to take our denominator, x squared plus 4x minus 12. We're going to set that equal to 0. So now we have a factoring problem on our hands. What multiplies to negative 12 but adds to 4, please? Positive 6, negative 2. So if x plus 6 is now set equal to 0, we have a vertical asymptote at x equals negative 6. If x minus 2 is set equal to 0, we have another vertical asymptote at x equals 2. Can we have 2 vertical asymptotes? Sure. That happens. All right, guys, how do we feel about this type of problem? Okay. Now notice that when we were doing this stuff back in chapter 2, usually the next step was, okay, now go over and draw the graph. But guys, we're prepping for a multiple choice test. It's going to ask you simply to find the vertical and horizontal asymptotes. What if, again, because you guys have done multiple choice tests before, what if choice B, for instance, said something like x equals 5, y equals negative 6, y equals 2? You think anybody might be tempted to say that's the correct answer? Because that would be wrong. Why is that wrong? 5, negative 6, 2. We just said those are the answers, but over here we said that this is incorrect. Why? Dallas? Yeah, because this is saying it's a horizontal asymptote at 5. These are saying, or I said that backwards. This we're saying is a vertical asymptote at 5. These are horizontal asymptotes, and we have that backwards. Okay, so I'm sure that you're tired of hearing me say this, but asymptotes are equations. We've got to get that variable in that correct location. So I've always encouraged people to think of it this way. So like x equals 5, for instance. That's going to be vertical because it crosses through the x-axis at 5. And y equals negative 6, that crosses the y-axis at negative 6. Y equals 2 crosses the y-axis at 2. Okay? That's the way 100 years ago somebody told it to me, and I've thought of it that way ever since. Hudson.
So what would you do if the leading coefficients were the same? How would you solve that?
If the leading coefficients were the same?
Or not?
Oh, the degrees you mean?
Yeah, sorry.
Yep. So if the degrees of the numerator and denominator are not the same, again, remember, we always have 3 options as far as how we approach those horizontal asymptotes. If the degree of the numerator is larger than the denominator, no horizontal asymptotes. Can't have it. If they're equal to one another, then just like we did here, we set up the ratio of the leading coefficients. And if the degree of the numerator is less than the degree of the denominator, that's when automatically the x-axis is your horizontal asymptote. It doesn't matter by how much, as long as the numerator is smaller degree than the denominator's degree. Okay? All right, so next up, number 6. Now this one may sound a little bit intimidating at first until we actually give it a second look and recognize that, okay, it's actually pretty straightforward, so long as we remember one little thing. Okay, so reading through it, it says that a polynomial of degree 4, I'm going to stop there for a second. If we have a polynomial of degree 4, how many zeros are we expecting? How many factors are we expecting? 4. Okay, good, so we haven't forgotten that part. Okay, so polynomial of degree 4 has coefficients 7i and negative 3 minus I. Okay, we want to identify the remaining zeros. So we are saying that we have a 0 here, we have a 0 here. So we know that we're expecting 4 zeros and we're given 2 zeros. So logic would tell us that we have 2, we need 2 more. We need the third and the fourth zeros. Now, we could turn this into a nasty problem to where I think of, all right, well, 7 minus I is a 0. Or I said 7 minus I, I'm sorry. If x minus 7i is a 0, then also x minus negative 3 minus I is also a factor. Could we multiply those together? I mean, we could play it out that way, but we're getting into some ridiculous steps. Why would we do that? Luckily, I think that we're going to remember that these complex zeros, don't they come in pairs? So if 7i, positive 7i is a 0, automatically what else is a 0? Negative 7i. Negative 7i. That's going to be 1. Now, if, same thing over here, if negative 3 minus I is a 0, what else is going to be a 0? Negative 3 plus. Again, complex conjugate. So, are we feeling pretty confident with that piece there? Notice that when we are talking about the conjugate, we're not changing all of the signs. That's been a mistake that some students have made in the past. They want to say that the conjugate of negative 3 minus I is just 3 plus I. That's not really the case. Again, all that we're changing is the operation. We're not subtracting, now we're adding, or vice versa. Okay, so number 7. We want to find all real zeros of the function. All right, now this could be, again, a multiple choice test. Again, we're going to be able to approach this in various ways, but this is the type of problem back in chapter 2 that we would have really treated this as a progression. So what I'm saying is that there are a lot of what might be deemed as extra things that we could do, but it's really going to be up to you. Could we go in and start and say, all right, the degree is 4? What does that tell us? Just like the last problem. We're looking for 4 zeros, 4 factors. Okay, it's always good to know. That also tells us what the graph would look like. Again, we could say, all right, positive leading coefficient, even degree. We know that by n behaviors, they're both going to be pointing up. Okay, great, but we're not drawing a graph. But it's good to know. It's good to keep this stuff in the back of your mind. Could we also jump into the Descartes' rule of signs here? So we're going positive to negative. There's one sign change to negative, back to positive, stay positive. So if we have 2 sign changes, what does that tell us? Somebody remind me, what does that mean? Exactly. There are 2 or 0 positive real zeros. If we wanted to figure out how many negative real zeros, what do I have to do there? Off to the side, we have to figure out f of negative x, don't we? So if we did this, and I would deem this as an optional thing, by the way. So we have x to the 4th minus x cubed minus 18x squared plus 16x plus 32 as I'm running out of space.